Here, we'll look at the relationship of hydronium ion concentration, hydroxide ion concentration, and Kw in acidic and basic solutions. Recall these definitions for neutral, acidic, and basic solutions. In neutral solutions, the hydronium ion concentration is equal to the hydroxide ion concentration. In acidic solutions, the hydronium ion concentration is greater than the hydroxide ion concentration. And in basic solutions, the hydroxide ion concentration is greater than the hydronium ion concentration. Remember, this is the ionization equation for water. This process occurs in every sample that contains water. This is the Kw expression. It states that the product of hydronium and hydroxide ion concentrations is an equilibrium constant called Kw. The concentration of H3O plus times the concentration of OH minus is always equal to Kw. This is true at all temperatures. However, the concentration of H3O plus times OH minus is equal to 1 times 10 to the negative 14th only at 25 degrees. In Chemistry 12, we can assume that the temperature is 25 degrees unless a different temperature is specified. So unless a temperature other than 25 degrees is specified, we can assume that the product of hydronium and hydroxide ion concentrations is 1 times 10 to the negative 14th. In pure water, which is neutral, the hydronium ion concentration and the hydroxide ion concentration are equal. And unless the temperature changes, this value of 1 times 10 to the negative 14th remains constant. Remember that all acids produce hydronium ions when they are added to water. For example, when the strong acid HCl is added to water, it completely ionizes to form hydronium and chloride ions. Let's add some acid to a sample of water to increase the hydronium ion concentration. We see that as hydronium ion concentration increases, hydroxide ion concentration must decrease in order to keep their product constant. In an acid solution, the concentration of hydronium is greater than the concentration of hydroxide, but their product remains constant at 1 times 10 to the negative 14th. It is important to realize that even though hydronium predominates in an acidic solution, there is always some hydroxide present in all aqueous solutions. Bases tend to produce OH- ions in water. For example, NaOH dissociates into sodium and hydroxide ions. Remember, in pure water, which is neutral, the hydronium ion concentration and the hydroxide ion concentration are equal. Let's add some base to a sample of water to increase the hydroxide ion concentration. A base is added and the hydroxide ion concentration increases. Notice the concentration of the hydronium must decrease in order to keep their product a constant. In a basic solution, the concentration of hydroxide is greater than the concentration of hydronium, but their product remains constant at 1 times 10 to the negative 14th. It is important to realize that even though OH- predominates in a basic solution, there is always some H3O plus present in all aqueous solutions. Knowing the equation for the ionization of water and the fact that the concentration of hydronium times the concentration of hydroxide is 1 times 10 to the negative 14th at 25 degrees, we can find the hydronium ion concentration in any aqueous solution if we know the hydroxide ion concentration by rearranging this equation to solve for the concentration of H3O plus. We divide both sides by the concentration of OH- and tidy up. And we get this equation. We can also find the concentration of OH- in any aqueous solution given the concentration of H3O plus by rearranging this equation to solve for OH- concentration. We divide both sides by the concentration of hydronium and tidy up. And we're left with this equation. From now on, we can use whichever one of these equations we need. But we must use caution with these. Remember, we can use 1 times 10 to the negative 14th only if the temperature is 25 degrees. If we're not at 25 degrees, we could not use this value for Kw. We would have to be given the value of Kw for the temperature we're working at. Even though hydronium ions predominate in acidic solutions, there is still some hydroxide ions present in all aqueous solutions. We'll show you how to calculate the concentration of hydroxide in acidic solutions. Concentration of hydronium is greater than the concentration of hydroxide in acidic solutions, but the product, concentration of H3O plus times concentration of OH minus, is equal to 1 times 10 to the negative 14th as long as the temperature is 25 degrees. We're asked to find the concentration of hydroxide in 0.25 molar HClO4 per chloric acid. Looking up HClO4 on the acid table, we see that it's a strong acid. Therefore, the hydronium ion concentration is equal to the acid concentration, which is 0.25 molar. We start by writing the Kw expression, concentration of H3O plus times the concentration of OH minus equals 1 times 10 to the negative 14th. We're not given the temperature, so we assume it's 25 degrees. We're asked to find the concentration of hydroxide, so we rearrange this equation to solve for the concentration of hydroxide. We substitute 0.25 in for the concentration of hydronium. So the concentration of hydroxide is equal to 1 times 10 to the negative 14th divided by 0.25, which is equal to 4 times 10 to the negative 14th. This is a very low concentration for the hydroxide ion. However, this is what we would expect in a strong acid where the hydronium ion concentration is high. Even though hydroxide ions predominate in basic solutions, there is still some hydronium ions present in all aqueous solutions. We'll show you how to calculate the concentration of hydronium in basic solutions. Remember, in a basic solution, the concentration of OH minus is greater than the concentration of H3O plus, but their product remains constant at 1 times 10 to the negative 14th. So if the concentration of OH minus is high, that means the concentration of H3O plus must be very low. We're asked to find the concentration of H3O plus in a 0.2 molar solution of the strong base SrOH2. Looking at the solubility table, we see that SrOH2 is soluble, and because it is a group 2 hydroxide, it's a strong base. We write the balanced dissociation equation for the base SrOH2. It dissociates into 1 Sr2 plus and 2 OH minus ions. The concentration of SrOH2 as a whole is 0.2 molar. The coefficient on OH minus in the equation is 2, so the concentration of OH minus is 2 times the concentration of SrOH2, which is 0.4 molar. Again, we'll assume the temperature is 25 degrees. In order to find the concentration of H3O+, we start by writing the Kw expression. The concentration of H3O+ times the concentration of OH- is equal to 1 times 10 to the negative 14th. Because we're asked for the concentration of H3O+, we rearrange the equation to solve for the concentration of H3O+. It is equal to 1 times 10 to the negative 14th divided by the concentration of OH-. Now we substitute 0.4 in for the concentration of OH-, and we get that the concentration of H3O+ is equal to 1 times 10 to the negative 14th divided by 0.4, which is equal to 2.5 times 10 to the negative 14th molar. Because SrOH2 is a strong base and the concentration of OH- is relatively high at 0.4 molar, we would expect the hydronium ion concentration to be quite low, which it is. Notice we have two significant figures in our answer. This is consistent with the value given in the data.